Hello everybody, and welcome to the Motion in a Straight Line unit of Physics 1101. Now a lot of people think of physics as being all about motion. There's actually a lot of physics that isn't about motion at all. But motion is an important starting point for physics, and it's going to be our focus for all of this course. We're going to spend the first part of the course on what's called kinematics. And in textbooks, that's usually described as the study of how to represent motion. I'll add to that textbook definition and say that it's really concerned with how we mathematically represent motion. Notice that it's all about representing or describing motion. It's not concerned at all with the how or the why of motion. That's dynamics. And after we've done some kinematics, we'll move on to dynamics, which is mostly about forces. The combination of kinematics and dynamics makes up the subdiscipline of physics that we call mechanics. Now, the word motion, I'm sure, is pretty familiar, but let's take a moment to just carefully define it. Motion is a change over time in the position or orientation, or both, of an object. So, for example, look at this falcon in flight. There are multiple exposures, and in each frame it's appearing in a different part of the picture. So it's clearly moved to a new position. So that's its change of position. Also, the orientation of its body is changing. Also, one more thing that we really will ignore most of the time, the way it's holding its wings and the way it's holding its head relative to its body are both changing. That's what you would call an internal motion. So we're not going to concern ourselves at all with internal motions, and in fact we're not even going to look at changes in orientation. We're going to restrict our attention to changes in position. This is what you call translational motion. So since motion is a process of change, we need to look at how things change. And if you're just talking about changes in position, or if you include orientation, there are a lot of different ways that position and orientation can change. So let's just take a quick look at a few examples. The simplest kind of motion to describe is straight line motion. And of course, straight line motion is all around us, but here's a particularly dramatic example. This is a rocket sled being used in a study of how the human body responds to large accelerations. Here's another common type of motion that we encounter. This is circular motion. And of course, the orientation of the motorcycle is changing, but that's not what we mean by circular motion. We mean that the position of the motorcycle is going around in a circle. The change in orientation of the motorcycle is a separate thing, and we can describe these two motions independently of each other. Now, in contrast to the motorcycle doing circular motion, here's a girl doing a head spin, and so she's not translating, she's just rotating. A lot of internal motion as well, but let's ignore that. So her center of mass, the middle of her body, isn't moving along, translating through space. All that's changing is her orientation. So this is rotational motion. Just as one more example, here's a base jumper being thrown out of a catapult. And so after they leave the catapult, this is an example of projectile motion. Now we're going to meet a tool that we'll use all through the course, and which I think students should be introduced to very early in their schooling. Perhaps the first time you ever start discussing motion in science class, be that elementary school or whatever. Nevertheless, most of you have probably never come across it. It's the idea of a motion diagram. And the idea is simple enough. You can think of it like a multiple exposure photograph, like either of these. There are two important points, though. The camera has to be stationary. It doesn't track the motion. And so if the thing is moving, it's going to appear in a different location of the picture during each frame. And we call the individual exposures frames. The other important thing is that the time between the frames has to be the same. We have a constant rate at which the frames are being taken. So this could be with an ordinary video camera, and perhaps you would have a time between frames that gives you 30 frames per second, right? FPS, you've probably come across that in standard video. When we actually draw a motion diagram, we'll use points. Now, let me just be clear. Sometimes you can actually use a camera to generate a motion diagram of a real motion, and you'll do that in the lab. But often we're drawing motion diagrams to help us think about motions. So then, partly it just takes too long to draw a picture of the object, so just use points to represent it. And we label the dots with numbers, which can be times, or they can just be a set of integers that show the order. And that's just to make clear which way the object is going. Now, in fact, we don't have to include those numbers. Later on, we'll put in velocity vectors, but for now, we'll put in these numbers to show the order. And so there's what the motion diagram for the Falcon would look like, just the dots with the numbers. Here's another one. Here are two balls, one being dropped and one being shot out to the side. And so there's the motion diagram of them. Now, the other reason we're drawing them as dots is that we're adopting something we call the particle model. And it's a model where we think of the object as if all of its mass was concentrated at a point at the center of the object. So this is a simplifying model. It helps us focus on what's important to us. If we're concerned with translational motion only, then things to do with the rotation of the object, changes of the shape, and so on are distractions. They usually don't affect the translational motion, and so using the particle model forces us to ignore those things. Let's just look at some simple motion diagrams. In 1D, there are only a few things that can happen. So one of them, here, I'll draw a quick motion diagram. And what I've done fairly carefully here is make there be equal distances between the points. So now remember that the time between points is the same. So here it moved this distance in a time, and here it moved the same distance in the same time. And so what we can conclude is that this thing is moving at constant speed. And what's more, what we'll get to is that it's moving at constant velocity. But more about that later. So I'm going to draw another example now. So this time, instead of just labeling with integers, I've labeled with actual times, presumably the times at which these frames were taken. But the thing to notice is that here, in this time, it goes a short distance. Here, in the same amount of time, it goes a much longer distance. So this is slow. This is fast. And so clearly this object is speeding up. And I just want you to think about how you would describe this motion. When you're describing a motion, there are several ingredients to give. One is a clear statement of the direction. So this is down and to the left, or even better, you could say that it is down 45 degrees below left, or something like that. That's clear. The other thing you would say is that it is speeding up. And so the two main ingredients to describing a motion are a clear statement of the direction and some statement about how its velocity is changing. Okay, I'm going to draw one more, and you can probably guess what it's going to be. So here this object is moving down, and you can see it moves a large distance in the first time interval, a small distance in this last one. This is clearly slowing down. There. So that's it for now. We'll add more information to our motion diagrams later as we learn some other tools. The ultimate goal is that we want to include accelerations on our motion diagrams. But we have a few other things to do before you'll see how to do that. There's one more issue with motion diagrams that we just need to deal with right away, and it's to do with what happens when an object reverses direction. Now, I mean, all the motion diagrams I've been drawing are for one-dimensional motions. And there's nothing, we'll use motion diagrams for two-dimensional motions, right? So for example, a projectile motion diagram might look like this. Right, so there's a quick motion diagram of projectile motion. But that's what I want to deal with right now, is when you still have a one-dimensional motion in a straight line, what happens to the motion diagram if the object turns around and goes back the other way? So here's a motion diagram where this object is slowing down. And now let's say it stops. Right? It's been slowing down. It stops and reverses direction. Well, if you draw the points for the reverse trip along the same line, then it can be very confusing. They can wind up right on top of the points for the forward motion, or they can end up in between them, but now it's very confusing to read. So what we do is, at the point that it reverses, we just displace the reverse motion slightly. So here it is now heading back the other way while speeding up. And so I'm going to repeat point 4 here. This object did not stick around here for very long. And you usually label these same point to make it clear that it hasn't actually just skipped up and then turned around, that we've in fact just displaced this piece of the motion diagram so it's not sitting right on top of this piece.